So the intensity depends on the solid angle, but we can define an averaged intensity that removes the dependency on the direction. The directional average is also called the mean intensity, and it's defined as J nu, which is the directional integral of the intensity normalized by all of the possible directions. And because the integral of the solid angle, the closed integral of solid angles is 4 pi, this is 1 over 4 pi times the directional integral of the radiation field. Now we can show that this quantity is related to the energy density of the radiation field. Consider the energy per unit volume per solid angle, where dE dV d omega is the energy per volume per solid angle. This volume here is defined by a light beam. So we can write it in terms of the velocity of light, the interval of time, and an area, where dA is the area that the radiation beam is spreading, dt is the interval, and c is the velocity that is traveling. So c dt is the distance that light is traveling in a unit time dt. If we substitute this volume, now let's call the energy per volume per solid angle, little u. Little u is usually given to the energy over volume, so let's give it a subscript omega for solid angle. So we can write that dE is equal to u omega c dt dA d omega. And using the definition of intensity, this has to be equal to the intensity times area per time times dt times the omega. Comparing both identities, we have that the intensity is equal to the energy density per solid angle times the speed of light. Now this, of course, is a function of the frequency. So we can give this quantity as a subscript nu for frequency. And substituting now the definition of the mean intensity, then we can write that the energy density of the radiation field is proportional to the mean intensity, as we wanted to show.